nanohub.org.
Online simulation and more for nanotechnology.
Welcome back to week 1, and this is module 4. And what I'd like to do, I guess, what we did in the last module is we obtained an expression for the conductance, and that's this expression you see here. And as I said, physically the way you think about it then is that conductance at a given energy. That is, the way you think about it is you have all these energy levels available for electrons to flow. And at a given energy, the conductance is given by Q squared times the density of states at that energy. Those are the lanes on your highway, divided by 2T. And T is the time it takes for an electron to get from left to right. So that's the conductance at a given energy. And the actual measured conductance is an average of that, averaged over energy according to this function, this derivative of the Fermi function, which, as I mentioned before, looks something like this, with a peak around the electrochemical potential. And if you look at the area under the curve, it's 1. So this is sort of like it averages this conductance over an energy range of the order of a few kT around the electrochemical potential. Now, so after this, when we talk about conductance, talk about resistance, we'll work just with this quantity, the Q squared D over 2T. The understanding is, well, that tells you the conductance at a given energy, and you can always average it over energy as needed. So I won't be writing this, carrying this integral all the way, all along. So I'll leave that out, and we'll just talk about this as the conductance. And what we want to see is how this conductance or resistance would change from the ballistic regime to the diffusive regime. This is where I try to connect back to module 1.1, where I said that there is this change in paradigm that is occurring as devices get smaller, that where we go from this regime where electrons move diffusively from source to drain to a regime where they go ballistically from source to drain. So if we write the conductance is Q squared D over 2T, so if I were to write the resistance, that would be something like 2T over Q squared D. Now, Ohm's law tells us that the resistance of something should be changing linearly with length. If I make something twice as long, the resistance should be twice as big. Now, the question is, can we understand that looking at this equation, the one that we just obtained? Well, what would happen if we took a conductor whose width is W, length is L, and for this discussion you can just assume a two-dimensional conductor. And if I increase the length, how do I expect the resistance to change? Well, first question you can ask is, how do I expect the density of states to change? And the answer is, well, in general, when you get to relatively big conductors, the bigger you make it, the more states you have. So if you have say, something that big, and this has, say, 10,000 states, and you add something that's equally big, that has 10,000 states, so together the whole thing has 20,000 states. So basically, the number of states, this density of states function, that D, just depends on the total area of that conductor. Area, or I guess if it was a three-dimensional thing, you'd look at the volume. In fact, that's why when we talk about big conductors, people don't just give you the density of states per unit energy, they give you the density of states per unit energy per unit volume. So this D then, we expect it to depend on W times L. Well, what about the time, the transfer time? The answer is that if you have ballistic transport, that's easy to think that an electron goes straight through. So what time does it take to get from left to right? Well, you'd think it should go as the length divided by the average velocity, which I'll write as u bar. That's the average velocity the electron takes to get from left to right. Now, average because usually in a solid, even in this ballistic regime, you don't have electrons all just going straight like this. It's more like some are going off at an angle. So you could have some that are going like so, some that are going like this, some that are going like this. And the ones that are going at an angle, as you might expect, would take a little longer to get through. And so what you need is this average. And exactly how this averaging is done and what you get, that's again one of those things we'll discuss in the tutorial. It's one of the homework problems I'll go through in the tutorial. But basically it is this velocity of the electrons times some numerical factor, which tells you this averaging. But the point is, what you expect in the ballistic regime is that the time will be proportional to the length. So this should be proportional to length. And what that means is that you'd expect the resistance of a ballistic conductor to be independent of length. Why? Because the longer you make it, the more states you have, because states depends on the length, on the area of this thing, but it also takes longer to get through the time. And those two just cancel out. So that is what that's not Ohm's law, but that's exactly what people see in ballistic conductors. That when you take ballistic carbon nanotube and people make these measurements, it's like you could make something twice as long, but it still has much the same resistance. The resistance doesn't change with length, as Ohm's law would have told you. And that you can understand from this picture quite easily by saying that, well, the time is proportional to the length, d is proportional to w, l cancels out. That's it. Now, how would you understand the traditional Ohm's law? Well, the way you could understand that would be if we think of diffusive transport. That is, when electrons are, like I mentioned before, when electrons are going through the conductor in a random walk. So one of the established results, and you can look this up on this discussion of random walks, is that when there is an electron is taking this random walk down, the time it takes to get from left to right is not proportional to length, but rather it's proportional to the square of the length. So, and the standard result is that the time for this looks like L square divided by 2D, where this quantity, which I've written with a D with a bar on top, that's called the diffusion coefficient. And the important thing is that the time is proportional to L squared. Now, in the literature, usually diffusion coefficient is written as D, and I put a bar on top because we have kind of used D already for another thing that's represented with D, namely the density of states. And so just so there's no confusion then, for density of states I'm using just D, whereas for diffusion coefficient I'm using D with a bar on top. So the point is then that for diffusive transport, the time goes up as L squared. And so one of the L's here cancels one, but the overall resistance then goes as L over W. Because this goes as L squared, this is proportional to L. The overall thing goes as L over W, and that's exactly Ohm's law. See? And so from this point of view, that's how you would understand it. That the difference between the ballistic regime and the diffusive regime is simply this dependence on length. Ballistic regime, the one that's very easy to understand, that when you're going like a bullet, then the time it takes is basically just your length divided by the velocity. Whereas when you are taking this random walk, like a drunken person, getting through, then it takes you a whole lot longer, and the time it takes is proportional to L squared. Now that is, as I said, if you have not seen this before, it's not obvious at all. So let me just try to say a few words about how you could understand the t proportional to L squared. Now it goes something like this. Supposing we have an electron that travels for a length of time tau. Tau is what's called the mean free time. That is the time that an electron travels before it hits something. And it travels with a certain velocity for this time tau, and the distance it travels is v times tau. And by the way, this v times tau is again something that people call mean free path. That is velocity times the mean free time. Although, as we'll see, the way we will define the mean free path is this quantity, but with a numerical factor, which represents some of these angular averagings that I talk about. But basically, it's this quantity. That's like the mean free path. So it travels for a certain length of time, tau, in this direction, and then it goes off in some other direction. And again, travels for a length of time, v tau. And then it goes off again in some other direction. Again, v tau. And again, v tau. So what you have then is a lot of random arrows pointing in different directions, all of approximately the same length, v tau. And when you add them all up, what you'll get is a random vector in some direction, but whose magnitude, because you're adding all these vectors, what you can show is that the magnitude squared, the distance that you travel, the overall distance, the magnitude squared will be equal to the sum of all these squared. So what I mean by that is the distance that it has traveled, I'll call that, say, L squared, would be equal to the sum of the squares of all of these. So each one has a magnitude of v tau. So that's like v squared tau squared. That's the magnitude. And how many of them do I have? Well, if the total time is t and mean free time is tau, then the number of individual vectors I have is like t over tau. So you can see then that L squared is proportional to t. Like I said, the time it takes to travel a distance is like proportional to L squared. And this is the quantity that is like the diffusion coefficient. So the time it takes is like L squared divided by the diffusion coefficient. So this would be a simple view of how you could try to understand that in the diffusive regime, time is proportional to L squared, or as opposed to the ballistic regime. And the ballistic one is, of course, much simpler. This is one, by the way, this is one of the points I'll be making in general, although this is just an incidental example of the point I've been trying to make, that actually small devices are easier to understand than big devices. Usually what happens is all our experiences with big devices, and then we try to take that experience and project it down to small ones. And that is why often small devices look very complicated. But if you did not have any such preconceptions, and if you just start from the basics and look at small devices and big devices, you'd find that the small devices actually are easier to understand. And this is one example of that. With a small device, what time does it take to get from left to right? Well, take the length, divide by velocity, done. Big device, you have got this diffusive conduction. How long does it take? Well, now you have to go through this whole theory of random walks to understand why it is proportional to the square, what the diffusion coefficient is, etc. It's a much longer story. Okay. Anyway, so getting back to the point then, it's like you can see now the difference between this diffusive transport and the ballistic transport. And what you could do is write in general then something like this, that T is equal to L squared over 2D. That's the diffusive answer, and plus L over U, that's the ballistic answer. So you could say that when you are talking of very small lengths, that's when this one dominates. When you go to big lengths, that's when the square takes over. And so this is the part that's the ballistic one. This is the part that's the diffusive one. Of course, it's not immediately clear that you could just add the two. So one way to justify it would be to say, okay, time is a function of length. So let us just sort of write it in a kind of a Taylor series. That is, okay, we have first a linear term, then a quadratic term. What's not clear is why we don't have further terms that we're adding to this. Okay? But in general, this ballistic and diffusive part, the whole physics could be captured with these two terms. And for short lengths, you get the ballistic answer. Long lengths, you'd get the diffusive answer. And if we use that with what we have here, then you'd get something like if I take this, I could write R as so resistance, it looks like there is a length term and there's an L squared term, but actually, of course, as I discussed earlier, the density of states itself is proportional to the length. And so, what I should do really is take one of these lengths out from here, put one there, take one of these lengths out and put it here. Which one could write as d divided by L. So this would be then like the density of states per unit length. Because as I mentioned, when you go to big conductors, the density of states grows proportional to the length. So this is density of states divided by length would be like independent of the length, if you like. And if you like, you could actually divide it by W as well and put a W here. So this is the quantity that's a material property. Doesn't depend on width or length. It's density of states per unit length. But the point is, from this point of view then, you can see how you get a resistance which has this a constant plus something that depends on length. And you could just manipulate this to write it like what I had written back in module 1.1. Namely, you could write this in the form of rho divided by W times L plus something that is on the order of plus a constant, which is something like a mean free path. But this is the part that I'll be getting into in the next module. That is what you can see that from here, you could manipulate it and write it in this form, where you would have a length plus some quantity. But what it is, and how we discuss this, that's the part that needs a little more discussion. And let me quickly, I guess, explain why this one is like a mean free path. It would be something like this. You can see that what is in here, if I pull this 2D out of here, it would look something like, some quantity times L plus 2D over U. That is, if I pull this 2D out of here, then it would look like L plus that quantity. And remember, this D is like V squared tau. This is the diffusion coefficient. As I discussed earlier, this is like that. Of course, there are numerical factors depending on angular averaging, etc., that needs discussion, like v square tau. But this one is like v. And so when you look at the ratio, that's like v tau, which is like the mean free path. So that's basically the result that I had sort of stated back in module 1. And you can kind of see now how, if you start from this expression for conductance, whose inverse is like the resistance, and then you make use of this idea that the time it takes to get through a conductor has two terms, the ballistic term proportional to length, diffusive term proportional to L square, then you automatically get an Ohm's law which has this additional term included in there.